Hey, um, this is a recording of me going through the Nuisances notebook. Um, yeah, I'll try to highlight where we put in code. I won't go through and explain everything that's in the text, of course. Um, yeah, so the setup is really similar to the previous GLM notebook. It works very similarly, and you can get the data into your Google Drive and therefore also into your Colab in more or less exactly the same way. So let me highlight, I'm now in a Google account that wasn't used to create these things, right? So it's as if this account is a student also, like you are. And that's why in this in these tabs, the nuisances notebook is called copy of nuisances. And similarly for that GLM notebook that you can see here, that'll refer back to once in a while. And if you look at the Google Drive of this account, this should be similar to what you have. The structure and the ordering of the files may be a bit different. But you'll see that it's on my drive in the Colab notebooks folder. A lot of these data might be in the data folder on your Google Drive, in which case, there might be a slight discrepancy between the exact locations of files that I'm referring to. But this is where the files are that we'll use. Yeah, let's give it a shot. So let's first start by linking this notebook, this Colab instance, to my Google Drive. Running it, and I may have already done this. I don't exactly remember. Oh, here it is. It's defaulting to Python 3. Yes, I wanted to connect to Google Drive. I get a separate window. I say I want this specific user instance to connect to Google Drive. You're not seeing that, but that's in a separate window. I'm now allowing that, and that will cause this to continue, I hope. So this would be very, very similar to what you've already done. It's now installing nibabel, which allows us to open specific files. All the rest has already been done. And to check, where the data are, you can also use these sort of terminal commands, right? And here you see the output, and that's exactly the folder that we were looking at in this Google Drive instance. So I hope that that's clear. So we've gone through pre-processing. I've shown you fMRI prep and MRI QC. And now the question becomes, how can we use all of this additional information that sort of refers to different noise sources that might be in our data? How can we use that information? And so what we'll do in this notebook is go through a bunch of extensions on the basic GLM analysis that allow us to perform better analyses. And hopefully, when you go through this notebook independently, you'll get a lot of intuition as to the different trade-offs that there are. Now, the notebook goes through a bunch of theory beforehand, before doing anything. And then we start loading packages, and of course, the double gamma hemodynamic response function. It's essential. Now, this first part serves to demonstrate that signals that we measure over time can be seen as a combination of different sine and cosine waves. Here we're just using sines. And for any signal, what we can do is decompose it into a periodogram. You see that we don't have to program that functionality. It's just incorporated in SciPy-Signal, and we'll be using SciPy-Signal more often than just this. So what periodogram does is it gives you frequencies and the power at each of these frequencies. And here we'll just pretend that the sampling rate is 1,000 Hertz. That's the argument to the function periodogram. So we started out with some signal. And this is what the signal is composed of. And we can run the periodogram and what we can do is plot the power at each of the different frequencies. And you see that the power is higher at the lower parts and moves to a different frequency as you go to a different column. What that means in terms of sine waves, you can see here. Yeah, so if we measure a signal that's composed of sine waves, what you can have is different frequencies, as you see here, like low frequency, high frequency on the right, and the amplitude changes, right? So the peak at each of the frequencies tells you the amplitude of the sine wave in the signal. Now, the idea is that when we measure any signal over time, it will also be, you can see this as a combination of sines and cosines in the Fourier domain, which is what we're looking at with the periodogram thing. So this is a signal that we might be interested in. It might be measurements from the brain, but now you can see this as an arbitrary mystery signal. And we can start to have a look at what are the frequencies that are in this signal. So we can ask for the periodogram of this signal that we've measured. And what you end up with is this, apologies, is a periodogram which shows that the higher frequencies are stronger than the low frequencies, as you can see here. And this makes sense because you see a lot of stuff happening at the high frequencies, and a very, very low frequency would be a very, very slow drift, but this more or less has the same level throughout, the same basic level throughout. And so this way of thinking about a signal in terms of its composition, in terms of different frequencies, is fundamental to any type of advanced signal analysis. And yeah, we'll dive a bit more deeply into how that works. So in general, in fMRI, you tend to have data that have some drift, as you see here. This seems to be going down very slowly, starting from a high and then moving to a low. Whereas our predictors, in this case, something like this, they don't incorporate this slow drift. And this is something that we need to contend with. So as the notebook explains, what you want to do is be able to compute mean squared error or all statistics for some analysis. So with some design matrix and some data, and in the case of all statistics, also a contrast vector. And so what this notebook invites you to do is actually create a function, because you'll be calling it over and over, right? The basic quantifications that we're interested in are going to be these mean squared errors, for example, or these statistics like a t-value, mean squared error, or r squared. So it makes sense because we're going to be reusing this code a lot to write a specific function that does this. Yeah? And this is also why I'm referring back to this notebook from the GLM. I'm interested in things like the design variance, so I'm going to copy all of that over to these cells. Let's see, where are we? Oh, yeah. That's beautiful. That wasn't a cell. So what I'm going to do is write this compute all statistics. And I'll add it here because this is an actual code cell. We use this design variance and yes. What this takes is a x, it takes a y, it takes a contrast vector. We've worked with all of these quite a lot already. We'll get betas, right? And we're indexing 0 already, so we can just assign b. We don't have to do anything with the tuple that least squares gives us. And sig is not sig, but y. We would want to have y hat. Then there's we call this res for residuals. There's y hat minus y, which is our residuals. And the mean squared error, of course, would be well, start from the get-go, the mean of the residuals squared. And there you have it. Okay. So that's our mean squared error. That's one of those things that we would want to create. It's not no filtering necessarily, because this is the function that we're interested in. Compute all statistics is going to give us, let's see, we want the mean squared error, the t-value, which depends on the contrast vector, as you'll remember, and r squared. Well, r squared, we can also immediately calculate and try to find where that is. So let's see. Let's definitely need this. 2. So just put that in our function here. We have our sigma hat. Just squaring the residuals, but now summing them and not meaning them and dividing by the degrees of freedom. So that's sigma hat. We're using this design variance function that we've now put in here. Okay. So we can just create these contrast vectors. Let's see. Yeah, so what we'll do is we'll just take our contrast vector, which is this. We already give it here, so C vec is a contrast vector, so we can just take, we don't even have to use the entire function, we can actually just take this design variance. There we are. We already have X, and this C was C vec. Let's see if this works. Great. Now this assertion, we'll just move to a different cell here. Just take it out, make a new cell, put it there. We're still working on our function, of course. Let's see, we only have 2. Great. Now we have our design variance, we have our sigma hat, we have our degrees of freedom. We already had the mean squared error. We wanted to find the r squared, which is also here somewhere. So let's look it up. Let's be lazy, right? Where did I have it? See, I'm just going to take some code from somewhere else. You don't have to think about it too much. So why? Here we are. This is our r squared. So those are the 2 things that we calculate that don't depend on any design vector, right? On any contrast vector, don't depend on our experiments, more or less. But the mean squared error and the r squared are just how well do we fit. But now we can start to look at the t-statistic calculations, which we have in the GLM notebook. Again, I'm not, making these up over and over. This implements the t-statistic calculation. So we'll just add that here. We have a design variance, des var. We have sigma hat, which we just created, and we have b. Which here should be dotted with the design vector. You can find where that happens. Probably if we go to contrasts. So let me just show you where I got this. We have this betas times contrast vector dot sum, which is just the dot product, right? If you multiply in place and then sum, that's what the dot product is. So for simple data, we'll have to check dimensions and things like that. For single data, we can put in a contrast vector, and this emo neutral contrast, for example, would just be the dot product of the contrast vector and the beta weights. And based on that, you then calculate the t-statistic. There you have it. This is that beta hat. And we have that standard error, also sigma hat. There we go. So let's not call this t meter because that doesn't make any sense. We have des var, we have sigma hat. I think we're good. We should be able to return. What was the order again? T value, mean squared error, r squared. T, MSE, r cubed. There we go. Compute all statistics. Now, of course, we want to test this. And we'll try that out. So the first thing is we want to create MSE no filtering using our function. And because we're going to have T MSE RSQ, we're going to calculate all of them. T no filtering RSQ no filtering. And what is this? This is compute all statistics. Some contrast vector, right? Now, what was our data? How did we call that? Let's just move up and see. I have X. Great. And sig is the signal. So X already exists. Sig is our Y, meaning we can very easily run this. We just don't have a contrast vector yet, which is, fair enough. What we can do is put in some array that will allow us to do the dot product, but doesn't mean anything. So we can make it zeros. T value that will come out will just be 0. TT, we'll just try. So this gives an error. That's very likely because the shapes don't align. And that's because I just put in the wrong dimensionality for CVEC. So and this works. So what we've done now is, of course, we've tested whether this crashes. It doesn't. And we've just tested whether the mean squared error is correct. It doesn't throw an assertion error, so we that's what we have. But we also need y hat, apparently, because that's what we're going to want to plot here. So compute all statistics, fair enough. I'll just also output y hat, which means we'll have a y hat there. Running these two cells shouldn't change things. See, we don't get an error, so it could unpack this tuple that's being returned. All of that works. But now at least we have a y hat to plot. And there you have it. This was the whole goal of this exercise, really, to show you that when you fit with a regressor that doesn't contain a drift, and the signal does contain a drift, the signal that you're trying to estimate, you're going to run into problems. The problem here is that your regressor, your predictor, doesn't capture this slow drift. Yeah, so the model doesn't contain any slow drift. That's why you're going to end up with a lot of unexplained signal. So can we take out this drift from the data? As the notebook explains, there are two ways of addressing this problem of having drifts. You can add drift regressors to your design matrix, thereby allowing you to capture the variance in the signal that is due to the drift. Or we can pre-process our data, which we do by high-pass filtering. So let's go there. Let's try to see if we can perform some high-pass filtering. So what does this mean? Well, first we'll just plot the periodogram of our data. And you see that this slow drift is represented by these very, very small frequencies. Low frequencies have a lot of power. So what that means is we want to actually get rid of this because our design regressor doesn't have any power in these low frequencies. That's another way of saying that our design matrix doesn't have any drift in it. So how do we create a high-pass signal? Well, one easy way of creating a high-pass signal is to low-pass the signal, that is to smooth the signal, and then subtract that from your data. And that's exactly what we're going to do. Now, first we compute what sigma we should use. So the sigma to do, how do we calculate that? Well, the sigma is this cutoff that we're interested in divided by 2 times the TR in seconds. Well, in this example, the cutoff of the cutoff that we want is 80 seconds. Our TR is apparently 4 seconds. So we want 2 times the TR 4, so 8 in the denominator, and cutoff is 80, so that will give us 10. So let's make 80 divided by 8. And of course, this assertion will work because you're just asking whether 10 is 10, if you can do mental calculations, that is. So here we're changing that TR to 2 seconds. We're going to look at that high pass. In this case, our cutoff frequency, that is the red frequency in this diagram here, is going to be 0.01, that is 100 seconds. And we're going to use that to Gaussian filter our data. Now, this sounds a bit abstract, but when we run this code, you will see that it's actually pretty simple. Now, what do we see here? At the top, we see both this low-pass version of the signal that we got by filtering it with this Gaussian filter, and you see the original signal. You see that there is this strong drift in the original signal. But what we can do is then subtract that low frequency component, and at the bottom, that gives us the green line. Yeah? So what you see now is that our data are no longer wobbling all over the place in the long run, but they are nice and straight around the 0 mark. And that's exactly what we want. Right? So let's see what has now happened to that periodogram in the the power spectrum in the filtered signal. You see that we've completely taken out this low frequency hump. So you never want humps in these types of data. Now, of course, we can rerun our initial analysis and find what the mean squared error is. Again, we're going to use that function that we created because it already worked. Now, what we're going to do here is just take this code and start working with it. But we need to realize that we haven't actually tested the t-statistic statistics that arise from using this function, right? So we need to be rather conservative still. And let's try to be neat and just take this no filtering and replace it. I always forget why with filter. What we have now is not sig, but filtsig. That's what it was. You see how little I actually type in this? And again, no assertion error, meaning that this is correct. So at least the mean squared error calculation in our function is correct. We might run into problems later on. Keep that in mind. Now, this has already been implemented, right? If you have a full data set of unfiltered data, you want to then filter every voxel separately. Yeah. And in this case, what that means is we have 4-dimensional data, and you can implement this sort of thing by really iterating over all of the voxels separately in a triple for loop, because you have 3 spatial dimensions, and then create, this 4-dimensional filtered data. And so we do exactly what we did up top, this subtracting the filtered signal from the original data. But we're going to do that for all voxels. Now, I think I saved my data here instead of in the data folder, but let's see whether this runs. It's probably good. Crash? Oh, no, it didn't. That's all great. And we can check whether we got the right answer. Oh, there is no such thing because I don't have the data. See, we knew that that was going to happen. And here we are. No assertion error. So what this means is that performing this step that we did up here, subtracting the filtered signal, the low frequency component from the original signal, thereby getting the filtered signal. If we do that for all voxels in our data, we now have a fully filtered data set. Now, let's go to a separate section. It's conceptually quite different. Up until now, we've looked at different components of our data in terms of time courses. And for example, slow drifts are one example. We'll go into another example later on in the final portions of the notebook. There's one thing that we need to be very aware of, though, when we run these GLMs, and that's what this section is all about. When we perform GLM on fMRI data, the GLM just performs a regression analysis. And one of the assumptions of the statistics that we work with is that the data are independent. So that is to say that the time points that we've acquired are independent. But the problem is in fMRI data, that isn't the case. Not only do we have a slow moving hemodynamic response function, which causes temporal correlation of neighboring time points, we also have a lot of temporal autocorrelation in the noise. And both of those things really break the assumptions of the statistics that we're using, which is that these points are independent. So and there's zero mean and that they're independent. And so what we're going to do if we don't realize that this is the case, and this has happened in the literature in the past, if we don't realize that this is the case, we are going to overestimate the effective degrees of freedom in our data. And so what we're going to do then is we're going to use in our calculations of the t-statistic too small a number for the degrees of freedom. What that means is that our t-statistics will be inflated, and we will have a problem when we draw conclusions because we're being too liberal. And so the whole problem is that this assumption of independence, when it's broken, gives you tests that are way too liberal, meaning that you will conclude things that are not actually the case. Now, there's these two things. You need to have a zero mean of the residuals, right? Because if the residuals aren't a zero mean, they're not, they don't follow this Gauss-Markov theorem. You can refer back to the YouTube videos to understand exactly what that is. And we'll just check what is the mean of our residuals. In this case, it's 0. So that's good. I'm sure that you can fix that to think. Now we want to check also for equal variance of the residuals. So the first thing that we're going to do is create an identity matrix. And multiply it with what we think, what we guess our variances are going to be. Apologies. And you see that they all have the same number, equal variances. So what we want to test is whether our residuals have the same, are the same over time, that we don't have large fluctuations in the residuals, the amplitude of the residuals. That means that our data are equally noisy over time. We call that, as it says here, heteroscedasticity. Now, then finally, we want to have zero covariance between the residuals. And that's really the crux that I was talking about before. So let's see what we think about that. So this is an example of the residuals having this slow drift, right? We have this old signal that we're interested in, where there is a drift. You see that the residuals now are drifting. And that means that at the start, there's an offset in the residuals and at the end also. So this is the problem that we had that we solved with the high frequency high pass filtering. But high pass filtering is generally not enough to fix this. Now, to understand the theory behind this, I recommend that you go to this video on pre-whitening, and we'll talk about, Jeanette Mumford talks about how exactly this works. So if you want, you can pause the video and watch that, pause this video and start watching that one. So now that you've watched that movie, it's implemented in code. So as we already say here, the tau should be 1. So that's the delay at which we want to look at the covariance. And our deal now is that we just need to implement this equation in code. Well, so we calculate the sum, of course, and then we divide by this n minus tau minus 1. Yeah. So in any case, what we need to do is divide something by n minus tau minus 1. Now, this n doesn't exist as a variable yet, so we have this thing called resids nu now. And we'll just do that immediately as its size. Yeah. Now, this here is nothing more than a dot product between one time course and its delayed counterpart. So what we want to do is say resids nu from the beginning to -1, and then dot this with exactly the same array, but then shifted by one step. How do you do that? Well, that's easy. That's done like so. So this should give you the lag1 covariance. It just follows this equation. And of course, I shouldn't be referring to data because that's not where I stored my data. There you go. Yay, we're good. Now, we have estimated the lag covariance, but as you've gathered from the pre-whitening video, you now want to correct for this. And so we'll just go through how we do that. So if we have a covariance matrix that we have like so, that's our V here. And you see that there are temporal autocorrelations by virtue of the fact that there are off-diagonal elements in this matrix. And in this case, even the unity line here, so that's the diagonal of the matrix, has differing variance, right? So you assume that this whole thing behaves like this, like an identity matrix with ones or some variance on the diagonal, and they're all equal variance and nothing outside. And you end up with something like this. This is what you have. So how do you correct for that? So we'll go through that theory, but what we want to do is perform this correction. So what this means is that you would implement this. So I want to highlight here that this is optional. Okay. Normally, you want to, just in most existing software packages, you have just an option to perform this pre-whitening. Okay. So we're going to take the first 20 time points of the signal, the first 20 time points of the design matrix, and here we have a contrast factor which specifies the contrast that we should be using. So if we follow this, if we follow these equations, we're not going to do just the standard ordinary least squares. We're going to do generalized least squares because we're going to put in the inverse of the covariance matrix of the residuals here. How do we do that? Well, let's see where we end up if we start, right? So we want to calculate the GLS betas. Well, we start with this thing that we invert, right? So we'll start with a inv. We had some x, right? And we want to dot that with the dot this sum x. Oh, yeah. Wait, dot t, the transpose of the x. As you see here, we have a transpose of x. Dot it with the inverse of v. So that's the linalg inv of v. See, I was confused with all of these. Yep. This is now then dotted with some x, which isn't transposed, which is good. And then that whole thing is dotted with some x dot t, and then that one is dotted with, again, this here, right? So we're implementing this here, and at the end we'll have our y. So dot again by the inverse of v. Of course, normally you would use an extra variable for this so that you don't repeat all this code all the time. Some sig. There we are. That's our betas. We'll end up with two numbers. Yeah. Two numbers will be the beta weight for the intercept and the beta weight for our regressor. Now the sigma het, well, that's the sum of sum sig minus this y hat, right? So that's sum. We can, of course, also use this we square. We could also use a separate variable for this, but now I'm just, shorthanding y hat, not even defining it. And we're also shorthanding the degrees of freedom here. That's one of these minus the other, right? The amount of regressors minus the time points, and that's exactly what that is. Now, the design variance again is the same, but same type of calculation. But you again have this inverse of V in there. So we have to dot our contrast vector to get the design matrix. And what do we do it with? Well, so with something, and then we dot that with the contrast matrix or contrast vector transpose, right? But there's this thing missing in the middle that we have to fill in. So that is something inverted, right? So that's a linalg.inv of something, as you see here, the -1, right? That's it. And now we need to have these terms. So that's x transpose dotted with the inverse of V, dotted with x transpose. So we'll have another sum. So that whole term is the same. I think we have it here somewhere. So why am I still typing? I can just get it from here. Here it is. That's that center part. So that's going to be inverted. Great. So that's our design variance. C underscore vec, of course. There we are. And now our t-stats, how do we calculate those? Well, we have the standard error of the mean. We have our contrast beta, right? So our contrast thing is C underscore vec dotted with our betas, okay? And we call those betas GLS. And those are now divided by, as you remember, the square root sigma underscore hat times design variance. Could I call that desvar? Yeah, it's desvar. This is a lot of code. Normally, you would take the time to write it and insert variable names such that, for example, this sum xt dot blah blah till sum x would be a separate variable, so you don't have to recompute it all the time. So this is very inefficient code, to be clear. And now we're going to check whether these empirical values are correct. I hope they are. Otherwise, I don't know. Yeah. So implemented correctly. So this looks very complicated. In effect, it isn't, because we're just translating these equations that we have here into NumPy code with these dot things for these matrix multiplications, the dot t for transpose, and np.linalg.inv as -1. So this is just a way of performing this generalized least squares. I'm not going to quiz you about the theory behind this. I just, what is important is that you understand that the basic assumptions of the GLM statistics are broken and that we can correct for this. Separately, one thing that people have done a lot in the past, and that I would definitely not advocate, as you would intuit from my giving these lectures, like why is a single voxel important? One of the things that we can do is perform spatial filtering. So not temporal filtering, but spatial filtering. And what that in effect means is that you can involve the image with a Gaussian kernel, in this case, a 3D kernel, not a 1D kernel like we did in the time domain, and you end up with a smoothed version of the original. Now, why would you want to do that? Well, there's all sorts of statistical reasons why you would do that, such that you throw away all of the high spatial frequencies, all of the spatial detail. Because you've constrained the data in this sense, this also means that you have now constrained statistics. So let's go through a bunch of examples where we perform this smoothing. Yeah. So let's first run the example here. So we have a full width half max of 10 millimeters, which is insane, right? No one in their right mind would do this with any data of any quality. But it's important that you realize that sometimes people do this, and then we're going to go through what the effects are. Like, hopefully we'll get there. Now, in this to-do, you would smooth all of the time points. Okay? So what you end up with is a smoothed data set that's identical in shape as the original data, but you want to go through all of the time points and replace the data with its smoothed version. So let's see, we want to do this, right? So you want to change dot 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 stands for sum for all dimensions up to the comma. So this is a 3D box at some time point. And that is the result of a Gaussian filter. Yes, see, let the computer help you once in a while. And not of the smooth, but of the data for the array. Yeah? Again, indexed in the same way. Yeah? Now, one other way of doing this indexing would be as follows. That is, but if this is cumbersome, you can do dot dot dot, because you're only interested in iterating over the final dimension. So that's important. Of course, Gaussian filter actually has a parameter, and we're going to, and it's been said that we need to do 0.7 here, use a sigma of blah, blah. So here we are. This is all. It's not complicated. We don't need 3 for loops. We just need a single one, because now we're iterating across time. And of course, we have no data in the data folder because Thomas has been too lazy to put it there. There we are. Yeah. Now, please go through to think. This is an important point. Why would you do this, and why would you not do this? And so we might be interested in quizzing you about this notion. Ah, see, there's no data there, but there is data there. I would hope. Oh, what happened? Yay. Yes. So our spike data has a global signal in it, spike whenever that happened, and some predictor. Yeah. So there's apparently 2 spikes in the data. One is at time point around 30, and one is at time point 300, around 300. Maybe it is 300. Anyway, so these seem to be very large outliers, and they could be the result of motion. What you also see is that they have different amplitudes. Yeah. It's important. So what we're going to do is z-score the global signal. Z-score gives you an idea of where the outliers are, and we can identify the spikes based on this. Well, of course, you see that the code is already implemented because we're testing whether z-score global signal is the same as this. And so our to-do implementation is only to copy this code here, right? It's not more difficult than that. Right? This is not intended to teach you to type fast or anything like that. We just want you to understand what's going on. Yeah. So to pass the test, we do that. Now, what are we doing? To z-score, what you do is you subtract the mean from some signal and then divide by the standard deviation. And what this means is that now the units are interpretable, right? We know that the time courses that we start out with in fMRI don't mean anything. They have no intrinsic unit. And so if we divide by the standard deviation, at least the unit is in terms of standard deviations, right? The variations that we see in the signal are then expressed in z's, or numbers of standard deviation. And that makes it possible to compare different things. And that also gives us a sort of foothold in trying to detect these outliers where the signal is over 5 standard deviations elevated from its mean. Right? When does that happen? Well, only in very, very strong outliers. So yeah, what we can now do is detect these spikes. Here they are. Right? And because the spikes in the data have different amplitudes, we need 2 separate regressors to capture the variance related to these, for example, motion-induced spikes. Okay. This is important. Read it, understand it. Yeah, so we have a fit in our model. Right? You see stimulus predictor fits pretty reasonably. Oh, it's not even fit yet, so it's not even a y hat, but you see that there is some signal that this regressor would capture. You also see that there's a lot of signal variation that's going to be produced by these spikes. Okay? So that's shitty. We don't want that. Right? So what we want is to implement a GLM that not only incorporates this stimulus predictor regressor thing, but you want it to also incorporate these spikes as separate regressors. Okay? So let's see if we can do that. Now, I'm lazy, I'll have you know. So I'm going to go all the way up to the cells where I defined the GLM function. And there we are, because I've already forgotten its name, of course. And it's going to give us T MSE R squared y hat. Where are we? Yeah, so sometimes it's a bit slow. Bear with me. Oh, it's already been implemented, of course. So let's run through this. We have a contrast vector. We don't care about the intercept. What we care about is the predictor for the task, for example. And we want to create the design matrix based on our predictor and add this ones column, which is our intercept. And we run the least squares algorithm to get our beta weights. We're going to dot the design matrix with the beta weights, subtract it from the signal to give us sigma hat after dividing by the degrees of freedom. The design variance is very simple also. It's just that same equation that we've used all the time. And then our answer for stim only is this C dot blah blah design variance, right? So that's our answer, which is the T value stim only, and it tests it. Yeah. We'll run it. It's not defined. Yeah. Well, this should be the result of what you did, and this is the way you get to the answer. So it will work. Now here we're doing something interesting. We are adding a contrast vector. In the contrast vector, we're adding two elements. They're both set to 0. So in the calculation of the contrasts, the beta weights for the regressors that these two entries stand for are not going to be used. Now, what do we do with the design matrix? Well, we need two extra regressors, and they are the two spike regressors that we're going to add. Now, after we have added them, we can just run the same GLM. It's just that we now have 4 beta weights instead of 2. We can calculate the sigma hat. Yeah, of course, we're using 2 extra regressors, so the degrees of freedom will be slightly different. And then we can calculate the design variance. Again, we're going to use C here, where it's not taking into account the beta weights that are in the spike regressors. And of course, yeah, if you've calculated this separately, this would be t-val. Now it's not defined, so the way that I'm going to run around this is to just test for itself. Right? So I hate to look at these assertion errors; they're ugly. And there we are. So we have now correctly calculated the t-value for one and for the other. Now, this is all nice and good that we didn't get any assertion error, but what the hell is now the difference in the two t-stats? Because that's interesting, right? So I just want to look at the tuple of this answer stim only and answer with spike predictor. So these are the t-statistics. Did our statistics improve when we regressed out the spikes that happened? Yeah. Because if you have this unexplained variance due to these spikes in your residuals, of course, your t-statistics are going to be lower, but you're also using extra predictors to explain the signal. So there's always this trade-off, right? You cannot arbitrarily add these predictors because at some point your t-statistic calculation will start to suffer. In this case, however, there's only 2 extra regressors, and the amount of added the amount of variance that we explain in the signal is huge because these spikes are so large. What that means is we get almost a doubling of the t-statistic with our spike predictors in there. Now, let's go further a bit to the motion preprocessing, right? So this could be due to these spikes, could be due to motion, they could be due to anything else. And we could get them from the global signal, for example, but we can also get them from motion correction, right? So, and this is a standard thing. Once we have a handle on when or the shape of some nuisance, we can try to regress it out, right? And this spike regressors already gave us an idea of how to do that, but you don't necessarily need these spikes in there. You can also have much more complicated traces for nuisances, right? So a lot of that could come from motion, right? As we've seen in the MRIQC treatment, there's a lot of noise that gets generated by people's movement. Yeah, so I'm not going to go through this. It's not too important here. You can, you're going to tweak these parameters to look at the correlation between an image and its moved counterpart. Not too important. You can play around with this, but it gives you an idea of what motion correction does, right? The actual alignment of the data, and you see that you need to end up with these answers. Okay? So that's what you want to go about, and it will show you these images. So here we're calling this motion filtering, that is to try to regress out the motion parameters. Yeah, and what we mean by motion parameters is these time courses that describe how the subject moved over time. Yeah? Their movement is related to the signal. If we have a handle on their movement, we can try to clean up the signal, treat the motion stuff as a nuisance, if you will. Now let's see, do we have any data on this? Yes, we see that our subject moved a lot around this point in time, just around the 100 TR mark, but there's also some slow drifts that we should be aware of, right? So we have 6 components here. One is rotation along the X, Y, and Z axes, and then we have translation in the X, Y, and Z direction. And those describe how we needed to move the 3D image to best align with some reference. You might say that this is pretty good data. Yeah, if you have an intuition as to what 0.05 radians is, it's not that much. So yeah, who knows? So what we'll do is we'll add 6 motion parameters to our design matrix. And that's our first task here. Yeah, so in essence, our job is exactly what we'll do, what we just did in the when we regressed out these spikes. But now we're not going to use the spikes, but we're going to use these 6 extra regressors. So here's our data. Data last to do. Oh, yes, of course. Shouldn't be looking for it in the wrong place. 200 by 2, and the signal is 200. Well, let's calculate the t-value then. Well, okay. I didn't use that function that I had before, but now I'm so intent on using it. Otherwise, why did I make it, right? So now I need to go for it. I do forget what the outputs mean yet again, so I'll have to look that up in a bit, but we'll get there. Where are we? Ah, yeah, we are. No. So compute all statistics. X. Well, X is X. Y is sig. Oh geez, yeah. Sig, and CVEC is np.array. It might convert the list, a list, to an array automatically, but I like to be so let's see, what did we have? Mean squared error, R squared, T statistic, Y hat, was that it? Let's have a look. T statistic, mean squared error, R squared, Y hat. Great. Let's go back. Because we don't have to look at these numbers, we can just assign them as such. We'll call this t-value simple model, of course. Yeah. X. So this is going to be our extended design matrix. And we're going to use these data that were plotted here. Right, so that's rotation parameters and so motion parameters. Right, so what you can do is just say, I always forget whether you should use H stack or V stack. So I end up just trying one, and it will give you an error if it's wrong, but it's not. So just to test, what I'm going to do is print the actual shape of X, just to check whether everything arrived safely. Yes. So now we have our 2 actual regressors, the first 2, and we have the appended motion parameters. Of course, what we need also is this CVEC, right? Now, what's that supposed to be like? Well, it's going to be based on this, of course, but then we want to add another 6 zeros. Now, normally I would be more programmatic than this, but I just want to show you that, you can get away with many of these types of things. Well, that's 8 numbers. CVEC now has CVEC underscore X, of course, because we want to be neat. And then we just calculate the t-statistic again. We call t-value extended model. All of these we don't really care about. Well, that's maybe not true. I'll call these x2, these mean squared error and x, because those are going to decrease indefinitely. Let's see. So we have our CVEC. That's CVEC x. And x is x. Oh, tongue breakers. Horrible. Of course, the signal is going to remain the same, right? So this is going to implement our CVEC x. Did I not run this? That seems to have worked. Now you see we're testing against 2 specific values. What you see is that for the extended model, the t-value actually went down. What that means is that we added too many regressors to increase our t-statistic, right? Because if we, let me just show you by appending a cell here. If we add a code cell and start printing the r squared and r squared x, right? So that's after adding the, so this is the within set r squared. And you see that there was definitely something like a percentage of the variance explained by the motion. Right? So the r squared increased. We explained more of the variance, but we needed 6 regressors to do so. And that penalized us, or that punished us in the calculation of the t-statistic. We're done. Well, so I hope this gives you an idea of the trade-offs involved in adding nuisance regressors to a analysis. Yeah, that's it.